So, let us again talk about certain more examples of harmonic loading. So, in this lecture as well, we will talk about certain corollaries of harmonic loading and also solve certain numerical examples to clarify the concepts of harmonic loading that we have learnt. So, in this lecture, we will complete harmonic loading and then move into next one. So, let us get into the. So, in the last lecture we have talked about the response of a single degree of freedom system due to a harmonic loading, that is a cosine or sine function, and we have learnt about magnification factor, we have learnt about the phase difference between the response and the forcing function. So, in another important application of analysis of harmonic loading is rotating unbalance. A rotating device or a rotating machine is very common in real life engineering. So, it can be a turbine, it can be a wind blade, it can be the rotor craft of an aircraft or helicopter, and in all these applications, in all these devices, we have a rotating component, which is a major part of this, part of functioning of this kind of devices. Now, since it is rotating, it is of course going to experience a centripetal force, which is nothing but the rotary inertial force or the rotary inertia that the body, the rotating device is experiencing. Now, when we have a nice rotating device, this inertial force or the centripetal force cancels each other, and the resultant of the force in horizontal or vertical direction is cancelled out, and therefore, the resultant vibration because of the rotation of this device is 0. But in most of the real cases, it is difficult to avoid any unbalance in the mass distribution of this rotating device due to manufacturing defects, due to some external particle getting attached to this rotating device. There is always a mass imbalance in this kind of rotating device. So, in this problem, in this figure that I have drawn here, I can see that I have given this black color point mass here, whose mass is m. So, this is an example where though this whole big mass m, mass with capital M, has a rotating device, is housing a rotating device, there is an unbalanced mass small m. So, this is an unbalanced mass . Okay. And this is going to produce a vibration for the system. So, let me explain the system in greater detail. So, this blue block that I have houses a rotating device, maybe a rotating machine or a turbine or whatever. Okay. And usually this kind of rotating machine or a compressor is placed on an elastic foundation. So, the elastic foundation can have a very simple model of a spring and a damper. So, I have modeled a rotating machine, say a compressor as a capital mass M with a spring K and a damper C. So, this whole thing, this capital M, K and C denotes a rotating machine. Okay. So, the blades of the rotating device is otherwise balanced, and the centripetal or the inertial force experienced by these blades cancels out each other, and there is no unbalanced force or no resultant force in the horizontal or vertical direction, and therefore, there is no vibratory load acting on the system, and therefore, the system is not going to vibrate. But because of some manufacturing error or some particle getting stuck to the blades, or due to some wear and tear, there could be a mass unbalance in this blades of the rotating device. This is a very common problem faced in many of the industrial machines. Now, what we have done is that we have tried to keep the problem simple. We have said that the total mass that is unbalanced is small m, and that is located at a distance e from the axis of rotation. So, this along this point is the axis of rotation, and the unbalanced mass small m is at a distance e from the axis of rotation. So, E is called the eccentricity. Okay, and m is the unbalanced mass. Now, what happens is that, let us assume that this whole rotating device is rotating with an angular speed of omega. So, it is rotating about an axis which is with an angular speed omega. So, omega is the angular speed or the rotational speed of the machine. Now, given this, because of this unbalance, is there going to be a vibration? If there is a vibration, what is the nature of the vibration and how do we analyze the vibration? That is what we are going to talk about in this part of the lecture. So, let us see. So, what we have done is that this capital mass m, we have restricted the horizontal motion of the capital mass m. Because of this two support, this two constraint, it cannot vibrate in the, so this vibration is cancelled out. So, we are constraining the horizontal vibration. So, it is only allowed to vibrate in the vertical direction. So, let us say that the displacement in the allowable displacement or allowable degree of freedom of the capital mass m is ut. Okay. So, now let us see what is the displacement. So, the capital mass m is experiencing a displacement of ut. So, let us find out the displacement of small mass m or the displacement of the rotating unbalance. So, that is going to move in the vertical direction by ut, plus it is going to move in the vertical direction by E into sin omega t, right, because it is at a distance E and the horizontal. So, this is the axis of rotation. About this line, it is the axis of rotation. This is the mass m. Okay, it is anyhow moving with a vertical displacement of ut. Apart from the vertical displacement, it is also going to have a displacement of this amount. Okay. So, this amount should be added to the vertical displacement. So, what is this amount? So, in time t, if omega is its angular speed, it must have travelled an angular distance or angle of omega t, and therefore, this distance that I am coloring with a red ink is E, nothing but E sin omega t. therefore, the total displacement, vertical displacement experienced by the or undergone by the small mass m is ut plus E sin omega t. So, this is the total vertical displacement of mass m. So, that is what I have written here. Okay. Now, knowing this, let me find out the equation of motion of this entire machine. So, if I find out the rotation of motion, equation of motion, sorry, if I try to find out the equation of motion. Now, m is the total mass of the machine, including the unbalanced mass, including the small mass m. Therefore, I can the inertial force on the entire machine can be written as m minus m into u double dot, okay, plus small m, which is also a part of the machine, into double time derivative of u plus E sin omega t, and then of course, I am going to have the damping force, which is C u dot and K u, and that is equal to 0. Okay. Right. So, m minus capital M minus small m is the total mass which is undergoing the displacement ut, and the small mass m is undergoing a vertical displacement of this. So, the inertial force is m into double dot of u plus E sin omega t. So, if I simplify this equation, I am going to get this as m u double dot minus m into E into omega square sin omega t plus C u dot plus K u is equal to 0. So, this can further be written as m u double dot plus C u dot plus K u is nothing but m into E into omega square into sin omega t. Now, if you look into this equation is nothing but the equation of single degree of freedom system with the right hand term, which is nothing but an equivalent to a force, a harmonic force F t with an amplitude of m e omega square into sin omega t. Okay. To solve this problem, we can adopt exactly similar procedure which we have done earlier for a generic case. I can assume that the steady state response or the steady state solution of the above equation, steady state response, let me call it as ut. I can always assume this as x into sin omega t minus phi. I can solve it in the similar way. I have to plug this into this equation, solve for x, and if you solve for x, you will see that x is going to be nothing but m into E omega square by k into h omega, where h omega is nothing but the magnification factor. Okay. So, instead of k, I can also write this as m into E into omega square, since k can always be written as m into omega n square, where omega n square is nothing but the natural frequency of the system. So, omega n square is nothing but k by capital M. Okay. And therefore, into h omega. and therefore, we can get the amplitude of the steady state response of a machine having a rotating unbalance operating at an angular speed of omega. So, you can actually find similarity between this solution. So, this is the final solution that we have obtained, and you can see a similarity of this solution with the solution that we have derived earlier. So, in earlier we saw x is nothing but a into h omega, where a is the static displacement of the system. Here also this is nothing but the static displacement because of a force which is equivalent to this term. So, with this we end the theory on rotating unbalance. So, now we are going to solve certain numerical problems which are going to help us in reinforcing the concepts that we have learned earlier. So, let us take this first example. So, we have done a similar kind of example earlier. So, in this example we have the same rigid bar of mass m. So, this blue color bar is a rigid bar which has an uniformly distributed mass m. So, there is a damper, so it is pin jointed about a point O. So, this is pin joint. So, it is free to rotate about the point O. So, at a distance L by 4 from the P joint, there is a damper of damping coefficient C. At a distance 3L by 4, there is it is supported by a spring with a spring constant 2K, and at a distance L by 4 on the other side, it is supported by a spring K. Now, the only difference between the earlier and this example is that there is a concentrated moment of the expression m0 cos omega t applied at the one end of the bar. So, what we need to find is the maximum value of m0 such that the amplitude of angular oscillation does not exceed 15 degree. If omega or the frequency of the applied moment is 400 rpm. So, let me re-explain the problem statement once more. So, for a moment, an externally applied moment m0 cos omega t is applied to the rigid bar. So, this is a rigid bar. We need to find out the maximum value of m0 that can be applied, provided that the maximum amplitude of the angular oscillation that this rigid bar is going to undergo because of this moment does not exceed 15 degree, and it is also given that the driving frequency is 400 rpm. The values of K, M, C and L are provided. So, let us try to solve this equation. The first thing that we need to do to solve this equation is to obtain the equation of motion of this system. So, in order to find out the equation of motion of this system, as we know, we have to, it is always better to draw the free body diagram. So, let us draw the free body diagram of the system. So, let us assume that it has displaced by an angle theta from its original position, which is shown by this dashed line about the pin joint O. So, let us now find out the moments and forces that are going to act on this rigid part. So, one is of course the inertial moment. So, let me call this as I 0 into theta double dot. Sorry, I O into theta double dot, where I O is the moment of inertia about the point O. So, there would be a spring force, because the spring has been compressed, there would be a spring force which is going to be 2k into 3L by 4 theta. The spring is compressed, so there is a upward force that is happening. So, similarly, there is going to be a damping force in this direction, which is going to be C into L by 4 into theta. And therefore, there is also going to be another spring force from the other end, which is K into L by 4 into theta. Now, if I write down the moment balance about O, I get I O theta double dot, and then sorry, I missed out drawing the externally applied moment, which is m0 cos omega t. So, when I write down the moment balance about O, it is I O into theta plus the force produced by this damping force, which is C L by 4 theta dot, that is the force into the moment arm of L by 4, plus the force, the moment because of the spring force, which is 2k into 3L by 4 theta into the moment arm, which is 3L by 4, plus the moment because of this spring force, which is k by L by 4 into theta into the moment term L by 4. And on the right hand side, I get the externally applied moment, which is m0 cos omega t. Okay. So, if I simplify this, I will get this as I O theta double dot plus C L square by 16 theta dot, plus if I calculate this, it is going to be 16, 9 into 2, 18 plus 1, 19 L square by 16 into k theta, which is equal to m o cos omega t. Now, let us try to find out the moment of inertia about O. Which is I O. So, I O is going to be m L square by 12 plus the distance from the point O, which is m L square by 16. So, that turns out to be 48 into 7 m L square. Therefore, this equation can actually be written as 7 m L square by 48 plus C L square by 16 theta dot plus 19 k L square by 16 into k theta equals to m0 cos omega t. So, this is my equation of motion. Okay. So, now I know how to obtain the steady state solution of this equation. I have to just assume that theta is nothing but, I have to assume that theta t is nothing but x into cos omega t minus phi, and substitute this into this equation, solve for x and phi. So, if we solve for x, x can actually be obtained as m0, which is the amplitude of the applied moment, by the equivalent stiffness into h omega, where h omega is nothing but the magnification factor. And k equivalent in this case is nothing but 19 k L square by 60. Okay. So, we know that the magnification factor has this expression, which is, I am just rewriting this. So, I have this as 2 zeta omega by omega n whole square plus 1 minus omega by omega n square whole square and square root of that. So, to evaluate this expression or to evaluate the magnification factor, I need the ratio omega by omega n and I need the damping factor. So, these are the two things that I need. So, I have to find out this frequency ratio omega by omega n and I have to find out the damping factor. So, let us do that. So, in order to do that, I have to first evaluate the frequency, natural frequency and the damping factor. Okay. So, let me try to find out the natural frequency. So, the natural frequency omega n is going to be k equivalent by m equivalent, okay, which in this case is going to be 19 k by 7 m by 3. All other terms are going to cancel out. So, this can actually be written as 19 into 3 into the value of k was taken as 5000 Newton per meter by 7 into the value of m was taken as 10 kg. So, if you evaluate this, you will get this as 63.8 radian per second. Okay. And the driving frequency omega, driving frequency or the excitation frequency omega is already given as 400 rpm. So, I have to convert that to radian per second, which is 400 into 2 pi by 60, which will end up being 41.88 radian per second. So, therefore, omega by omega n is going to be 41.88 by 63.8, which is equal to, I had evaluated that, and that is equal to 0.656. So, this is going to be 0.656. So, now our next job is to find out zeta. So, how do I find out zeta? So, I know that 2 into zeta into omega n is going to be C equivalent by M equivalent. In this case, it is C. L square by 16 is going to cancel out. So, I have C into 3 by 7 M. So, C is given as 450 Newton second per meter into 3 into 7 into 10 kg, and that ends up being zeta will become 0.15. This is the value of 2 zeta. So, zeta is going to be this divided by 2 into omega n, which is 450 into 3 by 7 into 10 into omega n into 2 into omega n is 63.8. So, if you evaluate this, this is going to come to 0.15. Okay. So, this is 0.15. So, if we plug these two values into this expression for magnification factor, you will get the magnification factor as, you can evaluate this for yourself, and you will get the magnification factor as 1.659. So, once you get the magnification factor, you can then say that x is going to be nothing but capital M0 by k, which is 19 k L square by 16 into h omega, and that x is given as 15 degree, which is in radians is 15 into 2 pi by 360 degree. We know the value of h omega, we know all these parameters. So, from this expression we can find out the value of M0, which will produce a maximum steady state response of 15 degree Celsius, 15 degree angle. So, with this we conclude this lecture. In the next lecture, we will again solve certain examples and thereby end the topic of harmonic loading. Thank you.